In this next section, we're going to talk about thermochemistry and thermodynamics, which is chapter 5 and 19. It's interesting that our book kind of has them on completely opposite sides of the book, but they are very much related, and understanding chapter 19 will help make some of the upcoming topics more understandable. So, thermochemistry is a study of chemical reactions and the energy change that it involves heat. Thermodynamics, on the other hand, is the study of energy and how it can transform into different types of energy. So we'll talk about that towards the end of the chapter. So thermochemistry is chapter 5 and thermodynamics is chapter 19. We're going to start by the first law of thermodynamics, and this is actually chapter 5.2. That says that energy can be converted from one form to another, but you cannot destroy it or create it. So whatever energy is out there right now is what we have, and you can't get more and you can't get less. So when we want to heat our home, we're converting chemical energy when we burn fuels to get it into heat that gets released. Sunlight is a type of energy that gets converted into chemical energy, right, as sugars when plants do photosynthesis. And so those show how energy also gets transformed, right? So thermodynamics. So some transformation happens there. When we start talking about energy, it can get a little complicated because energy moves from one space to another. And so we want to keep in mind what we're talking about. So the first thing we'll talk about is defining something called the system. The system is the thing in the universe that we're studying. So if we're looking at this piston right here that has some gases inside of it, the gases inside, these are the system. We often think about the system as the reaction that's occurring. An open system happens when both heat and mass can leave, basically. So if this piston didn't have a top on it, then I could have those gas molecules can leave, so mass leaves, as well as if a chemical reaction is happening, the energy involved in that could also leave. A closed system happens when you only have heat that gets exchanged, but the mass stays in. So this would be like if you had a coffee cup, right, that had a lid on it. It's not like over time that coffee is going to cool down, so the heat can escape, but the coffee stays inside. An isolated system happens when both heat and mass cannot leave and escape to the surroundings, so they're trapped inside. If we look at this image here, then the system is the gas inside that we're studying, but the surroundings are everything outside. So both the piston here and everything outside of it. So when we think of a chemical reaction that's happening, oftentimes we're measuring it, right? So if I put my hand right here, right, and I feel energy, maybe it gets hot. So energy is leaving, and I'm feeling that warm my body is the surroundings. So oftentimes it's hard to distinguish because we're so like ego focused that we kind of feel like we're the system, but we are the surroundings. And we're making observations about the system or the chemical reaction. Now we're going to define something called internal energy, which is the sum of all of the potential energy and kinetic energy within a system. So potential energy could be, right, the height of it when we think about physics, right, how high it is and how much it could fall, but it also has to do with chemical bonds that are stored in there. And then kinetic energy is anything related to movement. So whether the particles are moving or vibrating, it could be the heat involved with it or light energy. So that both of those are included when we think about internal energy. We just represent it with the letter E, and generally we don't actually know E at a given point, but we only know how it changes, or delta E. So here, if I have a reaction happening, initially I'm hydrogen and oxygen, like I saw in that piston, chemical reaction happens, and my energy goes down, and then there is a change in energy that I can measure. And usually the way we're measuring that is with both the heat involved as well as the work. So the reaction, or the equation you need to know, is delta E, the change in internal energy, equals the heat involved in that reaction plus the work. And work is a little bit trickier to think about because heat, we know heat, right? We feel warm, we feel cold, we can think about heat more tangibly, but work has to be done oftentimes with a gas in chemical reactions. It's a little bit different than when we're talking about, if I'm going to do work and I'm pushing a force over a distance. That is true because work equals force times the distance that it's applied. But in this case, we're not going to think about that in that way. We're going to actually think of it for gases, which is work equals negative pressure times the change in volume. So let's talk about what work looks like when we're thinking about gases. So if I had a table, I would know that I'm pushing on the table with this much force over this certain distance that it traveled. So that's a little bit more straightforward. But when we're talking about gases, there's a positive and negative sign associated with it. But you can think about it in the sense of, here I have a gas inside, right? That's our system. So we need to think, is our gas doing work, or are the surroundings doing work? So if we think about, is the gas doing work? Well, that would mean that the gas is pushing out onto the surroundings, in this case, this movable piston, and the volume is going up. So if my gas is doing work, then we know that my change in volume is positive. It went up. So then when I plug into my equation, work equals negative force times change in volume, here being positive, I have a negative times a positive, is going to equal a negative. So when I have negative work, that means that work is being done by the system, or in this case, by our gas. If work is being done on the system, well, that's kind of like the surroundings are doing work. So work being done on the system means the system is being pushed on. The volume is actually decreasing. So we'd have work equals negative, that shouldn't be force, that should be pressure. Should be pressure times negative volume because the surroundings did work and my volume decreased. And so the work is positive. So when I have positive work, work is done on the system by the surroundings. So we could even say that, by surroundings. So that's work. So hopefully that little tutorial kind of made sense about the signs of work. Is it being done on or by the system? Again, by the system means the system's pushing. On the system means the surroundings are pushing. We already are pretty familiar with heat. If I add heat, then the system is going to get hotter, or it's going to gain the heat. If the system loses the heat, it's going to get cooler, right? So gain and lose, positive, negative, that makes sense. And then we add these two together, add the heat and the work together to give us the total energy value. And that will tell us, did the system gain energy or did it have a net loss of energy? So let's practice. We have two gases in our cylinder piston arrangement, and there's two gases and they form a solid product C. As the reaction occurs, the system loses 1150 joules of heat to the surroundings. The piston moves downward as the gases form a solid, and the volume of the gas decreases. And there is 480 joules of work involved. It says the surroundings did it, which makes sense, right? The volume went down because the surroundings are pushing on them. So what's the change in internal energy? So we're going to go here and think E equals Q plus W. And the key thing is here, we know the numbers, but we just need to think about the signs. So we'll do E equals, we know the heat value here is 1150 joules, And it said that the system lost that much heat. So when we're thinking about our system, if it lost the heat, then that is a negative sign for the heat. Now we're going to put plus W. And then it says that the surroundings did 480 joules of work, right, because the volume decreased. So I would like you to get in the habit of using the work equation, negative pressure times change in volume, to figure out the sign. So we know that it's negative P times the volume went down, so times a negative. So negative times negative equals a positive value. So we have a positive 480 joules involved. So when we calculate that out, we measure negative 1150 joules plus 480 equals negative 670 joules. Okay, we have another one here. I would like you to pause and try this one on your own if you haven't gotten that habit yet. But we're going to calculate the change in energy for a process which the system absorbs 140 joules of heat from the surroundings, and the system does 85 joules of work on the surroundings. So the system now is doing the work. So let's do our calculation. We have energy equals Q plus W. We'll look at each of those separately. So the heat, the system is absorbing, so that means it's adding it in. So positive 140 joules plus, and now we have work equals negative pressure times volume, change in volume. And the system did work, which if we think about our piston, the gas inside, the system's doing work. So the gas is pushing up, and we're going to increase that volume. So we're going to have times a positive change in volume. So we'll have a negative sign here. So plus negative 85 joules. And you can go look at the chart just to double check, but I do want you to get in the habit of like conceptualizing in your brain what this means. So we're going to do 140 minus 85, and we get 55 joules. All right, now we're going to talk about more of a calculation one. So we have a fuel burning in a cylinder that has a piston. It emits 430.5 joules of heat. The volume of the cylinder is, it starts at, I'll just kind of do a little picture, 0.250 liters, and the final volume is 0.98, so we know it went up. If the piston expands against a constant pressure, you know the pressure here is 1.35 atmospheres. What's the change in internal energy? And then they give us a conversion factor we're going to use in a minute. So let's practice. We have our equation. We want to know the internal energy. So E, let's actually change in E, equals Q plus W. Now they give us Q, right? So emits, so that means a negative, so negative 430.5 joules. But they don't just give us the work value like they did before. We actually need to calculate it, which maybe actually is easier because we have the signs that will be calculated rather than kind of conceptualized. So we'll have negative pressure times change in volume. So we'll do negative, our pressure is 1.35 atmospheres, and our change in volume is going to be final minus initial. So it ended at 0.98 liters, and it started at 0.25 liters. So we're going to calculate that, and we end up getting, so if we multiply this all out together, the work we get is equal to negative 0.9855, and the units are atmospheres times liters. Kind of a weird one. It's a combo unit, just like density, which is like grams per liter or grams per milliliter. This is atmosphere time liter. That's fine. But we have our energy in joules, so we can't have our work in atmosphere liters. We actually need to convert it to joules. So It's going to do a quick little conversion factor. We want to get out of atmosphere liters and into joules. We can use our conversion factor that says 1 liter atmosphere equals 101.3 joules. Do that calculation and we get, and don't forget the negative sign here, my bad, is negative 99.8 joules. So now we can plug that in. So we have negative 430.5 plus the negative 99.8 joules. Add those together and we get negative 530.3 joules.